Welcome to the Quantum Gravity channel.
So, in this talk I will review purely virtual particles or fake particles or facons, and then we will move to the results of my recent paper about dress propagators with purely virtual particles, as well as ghosts and ordinary particles. So what are purely virtual particles? They are non-particles in some sense. That means they are particles that have no classical limit. And that means they cannot be obtained by quantizing something classical because their nature is purely quantum, and they can reach the classical limit only by producing effective interactions, micro non-local and micro acausal, among the other particles. So we'll see that with the new diagrammatics, which is my last but one paper. That is, I think, the best way to formulate them in a way that can be even implemented in softwares to make hard computations and predictions. Aside from that, the main application of this idea so far is a formulation of a consistent theory of quantum gravity. By that I mean renormalizable and unitary. And a lucky situation is that it is experimentally testable due to its sharp prediction of the tensor to scalar ratio in inflationary cosmology. I will not talk about that here. Not only, but the idea can also be used in phenomenology, collider physics, assuming that such non-particles exist and have light or relatively light masses. Then they can offer ways to model new physics beyond the standard model based on new inputs and evading common constraints that limit the applicability of usual particles, or they offer a new possibility to solve discrepancies with data. So this is the general situation for the moment. So in the talk I will first review the basic principles of the idea, and I will give you the diagrammatics which is used to formulate it, and then I will concentrate on the resummation of self-energies into dress propagators, and I will compare what happens with physical particles, ghosts, and facons. The main point of this part of the talk is that the peak region is outside the convergence domain of a series that is a geometric series, so it has a convergence domain. And normally you can reach it in physical particles, but only thanks to analyticity and only if you do not separate the observation of the particle from the observation of its decay products. So we will see that the kind of mathematical problems that we will describe arise also with physical particles. And actually we'll also see that they arise necessarily. It would be wrong for quantum field theory not to have problems. So first of all, I will tell you the thing that happens with purely virtual particles, and then I will comment on the muon. So basically, in the case of purely virtual particles, you cannot mount the particle because it is purely virtual and it refuses to be brought on shell. And so around the peak, you will see a sort of uncertainty principle like this one here, which means that basically no matter how precisely you prepare your in states, the energy I mean, you will not get a predictable plot around the peak. And you will see some uncertainty. This is interpretation. I will discuss that. But so it is crucial basically to make calculations with an uncertainty on the energy, because if you do not introduce it, you get meaningless results. And you might be surprised of this if you think that it is a new thing. So I will show you that it is necessary even to explain unstable, long-lived particles like the muon. And actually that it is necessary because it's absolutely impossible by the energy-time uncertainty relation to observe an unstable particle with no resolution, with infinite resolving power on the energy. Simply because to have a precise measurement on the energy, you need an infinite time, and you don't have it if the particle decays. So first I review the basic principles of the idea, starting from unitarity. What is unitarity? It's just the statement that the scattering matrix S should be unitary. And if you separate the identity, you have the optical theorem, and with a complete set of states, physical states from your space of physical states, V, this is the formula. So the forward scattering amplitude is a cross-section, in particular it is non-negative. The good thing is that you can reduce that to a set of diagrammatic equations. And they involve the diagram, the conjugate diagram, and a set of cut diagrams. And by cutting the diagram, you see what propagates on shell, because the cut propagators are on shell. Okay, from this example here, of this identity, you see that since in this process you just have the propagator, the real part of the propagator should be non-negative, so because it is a cross-section, and this constrains the object we can introduce in our theory. Now, if you happen to have a theory of ghosts and things that are wrong, here you will see minus signs in multiplying in the sum, and this is wrong because you need something positive. And so you might have to remove those objects from the space. The space of physical states will be a subspace of the space you start to quantize your theory. Now, I will call projection a removal of states that is consistent with unitarity. So that means that if you remove some states from the in and out states, and that you can always do, that's up to you, they should disappear automatically from the completeness relation in the intermediate states. Otherwise, this equation will not work. So examples are the Faddeev-Popov ghosts, the longitudinal temporal components of gauge fields. They work like that. They can be removed, and the consistency of the projection is ensured by gauge symmetry. Another example is the case of Leavitt ghosts. Leavitt ghosts decay because they have a width, and then you are assuming that you restrict in and out states only to the sets of stable states that do not decay. And then you will see the unstable states disappear also here inside, and that is consistent. So this is something I call Veltman's projection. But you have to reduce the S matrix to stable states. And in this case, these ghosts, Leavitt ghosts, they call abnormal particles, they should be unstable. Now, in the case of facons, instead, the consistency is assured by a new diagrammatics, which I review right away because it's, in the end, rather simple. So physical particles has this kind of propagator, which you can separate in a virtual and on-shell part. This is right, because it satisfies the inequality due to unitarity. In the case of ghosts, there are two types of ghosts, essentially. One has a minus sign in front, but the prescription is the same. Then you have a minus sign in front of the delta. That's wrong. This violates unitarity. Then you have the Leavitt ghosts, where you have minus sign in front, but also minus sign here, and then the sign here is okay. And then you have purely virtual particles where you have 0 in front, and that's also okay. There is a caveat, though, that if you study those two inside Feynman diagrams, it's straightforward. You just integrate on real energies and momenta as you normally do. But if you study those two, you need something new, which is either the Leavitt prescription for Leavitt ghosts or the new diagrammatics I will tell you in a moment for facons. And that's No, they are okay, but only if you consider strictly asymptotic states, which means that you have to let them decay. So at the level of an effective field theory, I have no problem with that, because it is okay to restrict to a subspace of states. But it's like saying that in the standard model, you should forget about the observation of the muon or something unstable. So as a fundamental theory, I wouldn't agree with Lienvik. And that's basically the difference, because once you have this delta function here, you can get rid of that very easily. And you can claim it is an unstable object, but it will not disappear completely. But the point is this, that normally people, unstable particles like the muon, they treat them as stable ones sometimes and unstable ones other times. And it's interesting to clarify what is going on. So I hope I can say something about that in this talk. So letting aside Levy ghosts, which will be discussed by myself in a paper that will appear soon, and with all the details and the comparisons with the other things, let me concentrate on purely virtual particles. So they start from a completely different propagator, you see. What is this new diagrammatics? At the tree level, it's very simple. Just take the propagator, decompose it, and eliminate the delta function. You start from the epsilon, Feynman I epsilon prescription, and then you drop the contribution that is on shell. And this gives this thing. If you go to loop diagrams, you have to start from the usual Feynman prescription. And then you have a procedure that I will describe now, which is very simple in the end, but it is not just some technical thing, where you basically make this decomposition in a clever way. There are many unclever ways to use this inside loops, so be careful. Many. But if you do the things that are written here, you also gain the decomposition of the optical theorem into a number of independent identities which hold true independently, on which you can play very clearly, because every threshold does not talk with any other threshold. So it's a very powerful thing. So another result that I will present that concerns all quantum field theories, actually, not just facons, is a set of algebraic identities that reduce the entire problem of unitarity to simple algebraic manipulations. And that, I think, is very interesting, because otherwise in quantum field theory you have locality, it's very easy recipe, renormalizability, very easy, algebraic, and then you have unitarity, which is one of the basic principles, but so far was formulated in a very cryptic way. So the thing you do is you ignore completely any integrals on the space components of the loop momenta. You work on integrands. You just integrate on the loop energies, and that's algebraic because you use the residue theorem. You do not do any other non-algebraic operation. Once you have done this, you decompose the way I told you. So you use this after point 2, not before. When you want to go to facons, you eliminate all the deltas that contain facon frequencies, and that's all. Well, there are some caveats, starting from the box, the pentagon, the hexagon, but for the bubble and the triangle, that's easy to illustrate, so we'll stop here with the bubble and the triangle. If you have the bubble, you have two propagators here. You just integrate on the loop energy, no space momentum, loop space momentum integration, you forget about that. And from two denominators you get one denominator, the sum of two terms, the other two cancel, and then you decompose it, principal values, deltas. If one of the two legs we want to be a facon, these two frequencies, one of the two or both, will be a facon, so you drop both the deltas. And that's it. And the result will be this one. So basically, this is a table you can write for the diagram, the conjugate diagram, the cut diagram, and there are two cut diagrams. And you apply the same recipe. And then you have in the column the diagram, and in the rows, the compositions by thresholds, by means of principal values and deltas, with this notation here. So basically, this is the diagram. It is this thing, -1 times delta, this delta, -1 times the other delta. Conjugate diagram, it's just the conjugate. Cut diagram, it has a 2 here, and the other cut diagram has a 2 with the other delta. So basically you see that every row is 0 independently, And this decomposes the optical theorem. So if you want to say that one particle inside is a facon, 1, you drop all the deltas that have 1. And when you drop the 2 rows, of course, the optical theorem will remain valid because every row obeys it independently. But when you eliminate those 2 rows, these 2 columns disappear automatically because they have just zeros. And they disappear, the interpretation is because they are cutting a facon leg. And the cut propagator of a facon is 0. Triangle, more complicated, but in the end it's the same thing. 3 propagators, integrate on the energies, you have the product of 2 denominators, a sum of many contributions. 2 denominators can be 2 principal values and no delta, 1 principal value and 1 delta. These are the 6 things here, or 2 deltas and no principal value. And you do the same for every diagram, and you will see that you will decompose the entire optical theorem into rows that are 0 independently. And then when you want to say that some internal leg is a facon, you just decide which one, and you will remove the corresponding rows. So for example, if leg 1 is a facon, you eliminate all the rows where you have a delta with index 1, which I recall delta is here. That means that you have a frequency of facon inside the delta, so you eliminate it. And once you eliminate all those rows, the one in red, some columns will disappear as well, and not by chance, they are exactly the columns that would have a cut facon leg, and they disappear because the cut propagator of a facon leg is 0, and so the entire cut diagram in that case disappears. And this is what you get when you have a triangle with just one facon leg, principal values and some deltas, but no double deltas, and so on and so forth. So if you want the generalization, just look at this paper and also the proof to orders. Now, let's see another problem that is, so a virtue of this approach is that it is completely perturbative. In the Leavick approach, you have to use dress propagators, by the way, because you have to make those things unstable, and that's crucial for the entire thing. And then in a reduced space, maybe you have some good effective theory. But here I want something that is good for all orders, and then if you have every order that is well defined, that you can ask yourself, okay, what do I find when I sum the basic series that you can sum in quantum field theories? There are few cases that you can resum: the renormalization group flow, the running couplings. This will not change with facons because the renormalization sector is not touched. Anomalies, same thing. And widths. The dress propagators instead change because this is interested by imaginary parts. So let's see. This is the physical particle, and this is the fake particle at the 3 level. Let me insert the epsilon here. That would be a principal value. And this is the ordinary ghost, not the Leavick ghost. This is just the ordinary ghost. And then you resum the self-energies. Self-energies will be some function of the momentum. I call it sigma. In the 3 cases, you have this formal resummation, this formal resummation, and this formal resummation. They seem different, but if you take epsilon, this mathematical artifact, to 0, some look the same. So what is going on here? Let's start analyzing what is going on. Oh, by the way, I will do everything in the approximation around the peak because the main things can be seen there and there is no loss of generality. So sigma can be approximated into a change of mass, a width, and a normalization factor. But the only thing that will be crucial for us will be the width. The other 2 things can be not paid attention to if you want. Anyway, this is the physical particle. And you see that you have the width has a sign that is coherent with the sign of epsilon. This is the ghost, and the width, which is non-negative here, by the way, the width is in this notation is non-negative, has the opposite sign. And in the case of facons, you find something different. Now, you can see that those two have the same limit when epsilon goes to 0. When epsilon goes to 0, they are the same, and this is suspicious, because this thing here, this 0 simplifies with that 0. At the peak, they are zeros, so a simplification of 0 over 0 is suspicious, and in the end, it is suspicious also because you cannot obtain from two different things the same sum, because if everything is meaningful, the sum could be expanded back to find what you summed, and this cannot. So what is going on? If you analyze the difference between the various things, for example, the difference between a physical particle and a ghost, and you do not throw anything away too quickly, this is the expression you get. And formally it is 0 when epsilon goes to 0. But if you expand perturbatively in powers of gamma, let me focus here just on the width. No z factor, no delta m, because they are irrelevant to the discussion. So just the width. And what you see is that if you expand in powers of gamma, the difference, the imaginary part, is an infinite sum of deltas and derivatives of deltas of contact terms. If you do the same for the facon, you find the same difference with a factor 2 less. Okay. So it's a strange object here, but it is formally something like that. Doesn't mean anything. It's just to be meant as a series expansion in powers of gamma. And it is this thing. And this is not a distribution. You can prove that this object is mathematically ill-defined. Now, in the case of physical particles, everything is well-defined, actually, because it gives the Breit-Wigner in that limit. And in the case of ghosts, since the difference is this object, you will have the Breit-Wigner plus that object. So what is that? And in the case of purely virtual particles, you will have the Breit-Wigner minus 1/2. Instead of 2 pi in front, you have 1 pi. So it is always around. And this object is not a distribution because you can act, for example, on a well-behaved function like this one and formally and truncate. Then the truncation, of course, is well defined, but when n goes to infinity, this blows. So what is the root of the problem here? The root of the problem is that the geometric series we are summing has a finite convergence radius. If analyticity is available, which occurs only in the case of physical particles, and only if you sum the cross-section for the observation of the particle and its decay products, then you can reach the region outside by analyticity starting from the region inside, the convergence region. This is the region, by the way, keeping epsilon. So if epsilon goes to 0, you see that the peak region is never good. But you can reach it from the convergence region for physical particles here, for example. Why? Because there are two nice features of physical particles. One is that the Feynman prescription is analytic, and the other thing is that this denominator never vanishes. Never. Because you cannot make the imaginary part and the real part vanish at the same time. So there are some problems, and they are very important because they also occur with physical particles, long-lived unstable particles like the muon, whenever you separate their observation from the observation of their decay products. So you can repeat the exercise for, again, physical particle, but now you separate the diagrams where the particle decays, which are these, from the diagrams, the diagrams where the particle is observed, because if you cut, these are the cut diagrams because I focus on the imaginary part of the amplitude, that for simplicity, but you can extend this to the real part. If you cut the particle, that means that the particle is on shell. You are trying and observe an unstable particle, which is kind of strange, but experimentally we do it. So we must be able to explain that. And the other thing is instead the case where the particle is not observed, but you observe its decay products, whatever they are. They will be cutting this bubble here, which can be anything, containing also higher loop corrections. So twice the imaginary part is the sum of two cross sections, basically, and you can calculate them because we have these approximate formulas around the peak, and these are the results. So the imaginary part of the propagator splits into the sum of these two objects. It's quite reasonable, by the way, that it's placed like that, but you can check it, making the sum. It's another geometric series, two geometric series. And when epsilon goes to 0, you find that there is no muon observation. You cannot observe the muon. This is the prediction of quantum field theory so far. And instead you observe its decay products. Now, this is consistent, but only if you understand that the outgoing states are literally at the end of time. So you take in states at -infinity in time and out states at +infinity in time, which is, by the way, also the thing you have to do with Liebig things. That's the only possibility to have something meaningful there, assuming that their prescription can be generalized to all orders, which nobody did, but it is possible. However, we observe the muon, so how to describe that process? Now, it is impossible, as we did. It's just impossible, because we are pretending that we can violate the energy-time uncertainty relation. Check atomic excited states. If you have any energy level that's excited in an atom, since it is unstable, you will never be able experimentally to find its energy precisely. That's a known fact, because it takes an infinite amount of time to determine energy precisely. And if it is unstable, you don't have that time. But the point is that in quantum mechanics, you can have a control on the uncertainty relations that are around, because you work on coordinates and you have also momenta, eigenstates. But in quantum field theory, you renounce that from the beginning. Basically, in quantum field theory, you are renouncing any determination of position and time to focus on energy and momentum. And so you are tacitly assuming that all of your states have a very precise, infinitely precise energy and momentum. And then you can put wave packets on the external legs, but that's not enough for the muon. So what we said is consistent, but only if you have that the process literally ends at the end of time. But that is in contradiction with the muon observation, which we observe because we have traces in detectors. And so if the problem is that we are trying and violate an uncertainty principle, that means that we are missing some uncertainty. We are assuming that it is 0. Let me show you how the problem manifests itself in physical particles. Just take this diagram. It's ill-defined. It means nothing. This diagram is this thing here. So this is the on-shell unperturbed delta function, the cut propagator. Then at one loop you have 3 diagrams. The sum of all 3 is okay, but when you separate the particle from its decay products, they are ill-defined. Let me show you, because here you have a propagator, here you have the conjugate propagator. This is this thing. This distribution is not a distribution. This makes no sense. So even term by term, without resumming, it makes no sense. There is a way actually to give sense to those things by splitting masses and making them coincide. So this I call the coincidence splitting method. You can define the product of principal values and delta functions. You can do that. Then you can redo everything term by term. Now term by term, it will make sense, yes. But the sum will not make sense. And the sum will be problematic, as was the object, the strange object we saw previously. So there is no way to escape here. The problem is there. And by the way, a check that this splitting method works is that you do not lose anything, because when you sum the observation of the particle and its decay product, you get back the Breit-Wigner that you expect. So you are not losing anything, and it works. But when you separate the two, there is no way of doing it. And I stress again, it should be so, because otherwise you would be in contradiction with basic principles of quantum field theory. Now, as soon as you introduce the energy resolution, the problem disappears indeed, as you expect if this is the correct interpretation, namely that there is some uncertainty behind that you basically have hidden in the formalism quantum field theory. So you can ask yourself, how do the formulas change if you take into account that processes occur within a finite amount of time? Well, basically delta E will enter everywhere, but in many places it will be negligible, Z and M, because it will just be a redefinition of things that are already there. And since you assume it is a small effect, you don't care. The only place where you cannot ignore it is when it goes into the imaginary part, because you start from zero there. It is zero at the 3 level. And so let me assume that the entire effect can be described by a certain shift of epsilon, after which you can put that to 0. And the form of this shift will not matter. You can write here any function of delta E you want, as long as it goes to 0 with delta E. It will be a redefinition of delta E. And the result is this. Now, the two things are both finite, non-zero. And you can consider the case of the Z boson, where the gamma is much bigger than delta E. You do not have a large uncertainty on the measurement of energy on the peak of the Z boson. So this is the inequality, and there you do not see the particle, you see its decay product, as we know. The case of the muon is this one. Gamma for a muon is 10 to the minus 19 GeV. 10 to the minus 19 GeV. So there is no chance you have a delta E be smaller than that. And that's where you see the difference, because now this contribution is crucial, and this other inequality basically tells you that this object is just a delta function. So basically that's correct. What we do is to treat the muon as a stable particle for many purposes. Under these conditions it is correct, and it is just a delta function. But it is correct, I stress, even after I resum the gammas, the powers of gamma in the dress propagators, which is normally not done. You just take the free propagator and you forget about the problem. So the conditions of convergence, radius of convergence of the series with delta E are these ones, and they are satisfied when this holds. So this is not a serious obstacle for physical particles, I repeat, because you have analyticity that allows you to cross the obstacle, but only if you sum the decay of the particle and its observation. When you separate the two, you have the problems, and you need to take delta E different from 0. Now with purely virtual particles, let's do the same. You shift and you check the convergence condition. The convergence condition is the same, by the way. I chose the notation. Here there is no factor 2 with respect to physical particles, precisely to have the same condition here, which is the one that makes sense. And but this time this is a serious obstacle. You cannot say I sum the observation of decay products and the particle, because there is no particle to observe here. So this is there and it remains there. And so its interpretation is again that it is rooted into a hidden uncertainty, possibly. This is the proposal of the interpretation of this. And that could be observed, namely, what happens if you try and observe these things. I will tell you in a moment what could happen. Okay, so this is the idea, that there is a fundamental uncertainty, because beyond this obstacle, you are really in a non-perturbative region. By the way, if you check the old books and papers by Veltman, Toft, Diagrammer, all of them are worried about being sure that the geometric series is convergent beyond the bound, that they can cross the bound, and they all justify it by analyticity. So they never take it for granted, never. Yes. Yes, you do not see a track differently from respect to the muon, and you will not even see a peak differently with respect to the z. You see the final products because you have to consider the facon as a mediator that is unobservable, so you can call them decays if you want. But if you arrange your process so as to go around the peak, too close to the peak, it will return an uncertain result. That's like saying that you want to measure position and velocity of a particle at the same time. You will just not be able to do it no matter what you do. This is... Sorry? Yes, and it will satisfy a bound. So here I will tell you in the next slide what happens. Let's see, in a few slides. Okay. Now, ghosts have a similar property. I will not comment on that, but that is to remind you that there is a crucial thing with ghosts because... So what is the reason for this in facons, by the way? Facons have a prescription that is not analytic. Taking those rows in the tables that I told you, removing the deltas, is not an analytic procedure. It is region-wise analytic. Region by region, the amplitude will always be analytic, and so on and so forth. It's not very bad, but it is non-analytic perturbatively. Instead, ghosts have the analytic prescription here. It's just the Feynman one. It's I epsilon. But after you resum, you see that there is an obstacle because you can set the imaginary part and the real part to 0 at the same time. With facons, by the way, the denominator never vanishes like physical particles. But with ghosts, it does. So let's see phenomenologically what you can do and what could happen. So first of all, you can always avoid the problem by choosing configurations that are far away from the peaks. If you choose the invariant masses of all the subsets of external states that are mediated by a facon, then as long as they satisfy this inequality where this delta E minimum is gamma divided by 2. Okay, gamma divided by 2 is delta E minimum. Then you can make predictions at arbitrarily high energies. But you cannot integrate on the phase space of all final states because you will necessarily cross that bound. So what happens there? You are in a non-perturbative region. So that means that you should know, and there is no shortcut to go around the problem. No analyticity, no tool. You are truly in a non-perturbative region. You know nothing about the non-perturbative theory. Anything could happen. I can just give some hints. First of all, I mentioned that if you put numbers in quantum gravity, you will not see effects of this because you more or less are in the situation of the muon, where, as we saw before, you can basically consider it stable and forget about its width. The width of the muon is so small that whenever you have a delta E, and you need a delta E, that's the thing, it will be much bigger than that, and then everything will work provided you do what I told you before. So the problem is, let's say there are some facons that are relatively light, like in the models we studied last year for collider physics. Then a form of this, so this epsilon squared of corrections, or delta E squared, this thing here, can be either the impact of your experimental apparatus, on which you will hardly have a control, or non-perturbative effects. So here I just show you that there exist forms that I can provide that are consistent with everything else we know about this object. For example, this thing, this formula here, which could be due to non-perturbative effects, or the apparatus, where delta E minimum, again, is gamma divided by 2. This is delta E minimum, in this case. So if delta E is related to gamma because it comes from non-perturbative effects, this one will reproduce what we know, namely the classical limit will be okay when gamma goes to 0, the bound will be satisfied, this bound will always be satisfied, so you can reach the classical limit because you will never violate the bound, you will never cross that region, and so on and so forth, provided you have this. And then if you plot an object like that, you will see the difference. That's huge with respect to a bright Wigner. The physical particle is here, that's the peak, but this thing will be suppressed and with a form that might be uncertain here because you do not know anything about this. Yeah, this is a power, and so this is the simplest function I can set. A power, provided the power has a certain bound, when gamma goes to 0, which means the classical limit it goes to 0, it reaches the classical limit that you expect without ever crossing the bound here. No. This is just a phenomenological guess of non-perturbative effects I know nothing about. This is nowhere comes from calculations. Calculations do not allow me to reach a non-perturbative region, so I just want to show you that there are possible answers for candidates for the non-perturbative effects that I cannot control. And a final comment is that this peak uncertainty has no relation with the violation of microcausality. So facons bring two new things into the game. One is the violation of microcausality, and one is this peak uncertainty. This one was expected, but let me stress that when I talk about violation of microcausality, it is not, as far as I understand, because it is not the same thing Lee and Vic talk about. Because as far as I understand, Lee and Vic talk about a violation of microcausality that is related to the gamma. This is related to the mass, not to gamma. In the case of facons, you have a violation of microcausality that is related to the mass because the principal value violates microcausality. There is nothing you can do about that. Even classically, you have here a principal value, something, not this. This is not the principal value, but you saw the principal value before. So if the propagator classical limit, for example, the principal value, the mass, you will have advanced and retarded potential, and the advanced potential will contribute to a violation of microcausality, and that is quantified by the mass. That is the scale. And it survives the classical limit. So if you drop the loop contributions, it will be there, because instead the peak uncertainty, which is given by the width, is a completely different thing, and it does not survive the classical limit because gamma goes to 0 in the classical limit, and that is the interpretation. So basically, in a propagator of a facon, you have a mass, which now has this interpretation. It's not a mass because this is not a particle, so it is the scale of the violation of microcausality. And you have a width, which is not a width because this is not a particle, and the width is the peak uncertainty. That's the interpretation.